we can use calculus to solve applied minimum and maximum problems. So here they are. One of the most common applications of calculus involves the determination of minimum and maximum values. So consider how frequently you hear or read terms such as greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, and greatest distance. Before outlining a general problem-solving strategy for such problems, let's look at an example. So a manufacturer wants to design an open-top box having a square base and a surface area of 108 square inches. As shown in this figure, what dimensions will produce a box with that maximum volume? So supposedly he has 108 square inches of materials to use, like he's limited to that boundary, but he wants to be able to make the box as big as possible. So how would we do it? Well, we know the base of the box is a square. So the dimensions of the square would be x by x times the height. So the volume would be x squared h. The surface area, we know the answer to the surface area, but given those restrictions also, the surface area is going to be the area of the base plus the area of the four sides. Remember, the top is not, the top is open rather. So the surface area is going to be the area of the base, which is x squared, and the area of each side is x times h. There's four of them, so that's 4xh. So the surface area is x squared plus 4xh, and that should equal 108. Because the box has a square base, we just talked about this, the volume is x squared h. That's the primary equation. And the reason we call it the primary equation is because that's the equation that we're trying to optimize. We're trying to find the maximum volume for this particular situation. The surface of the area, surface area of the box is, like we just said, x squared plus 4xh equals 108. That's the secondary equation. Usually in optimization problems, you're going to have an equation that you want to optimize, and there's also a secondary equation that relates the variables involved in a different formula as well. So because v is to be maximized, you want to write v as a function of just one variable. To do this, you know the answer to the surface area equation, so solve it for either x or h. In this case, it's going to be a lot easier to solve it for h because there's just one term with h in it. So subtract x squared, then divide by 4x. So 108 minus x squared all over 4x. Once you do that, you have h in terms of x, then you can substitute that into the volume formula to get the volume formula all in terms of x. Why is that allowed? Well, because these two formulas, the volume and the surface area, are for the same box. So the x's and h's for it should be the same. Okay, so I substitute the 108 minus x squared all over 4x in for h in the volume formula. And then you simplify it. Notice a factor of x will cancel here and here. And then you would have 108x minus x cubed all over 4. And divide both those by 4, you have 27x minus x cubed over 4. So before finding which x value will yield a maximum value of f, you should determine a feasible domain. In other words, what values make sense in this problem? Well, you know that the volume has to be greater than or equal to 0. In fact, it actually has to be greater than 0 because if your volume was 0, that wouldn't be very helpful, would it? So you also know that x must be non-negative so that the area of the base is area equals x squared is at most 108. So the feasible domain is that x should be between 0 and square root of 108. Okay, because if you made x bigger than the square root of 108, it would force the height to be a negative number to make the formulas work out. But height can't be negative in a real world situation. So as I normally did before, you solve to get the maxes and mins by first finding critical numbers of the first derivative. So take the first derivative, set it equal to 0, and then solve for x. You get x is plus or minus 6. So those are the critical numbers, but we throw out negative 6 because we're talking x represents feet. It's not inside the domain either. So evaluating v at the critical number x equals 6 and at the endpoints 0 and 6, or 0 and square root 108. Now the endpoints 0 and square root 108 are both going to produce volumes of 0 because that's where you put all of the material in for the height or all of the material in for the base, and it makes the other dimension go to 0. So the only other thing is when x is equal to 6, and that's the dimension for the base. So that volume is going to be 108. So V is a max when x equals 6, and the dimensions of the box are 6 by 6 by 3 inches. And you can get that by substituting 6 back into the surface area equation originally and getting the height, and you would get it that it's 3. So in example 1, you should realize that there are infinitely many open boxes having 108 square inches of surface area. To begin solving the problem, you might ask yourself which basic shape would seem to yield a maximum volume. Should a box be tall, squat, or nearly cubical? So here are just a variety of different boxes and the different volumes that you would get for each of them. Okay, which box has the greatest volume? This one does. Remember that you're not ready to begin solving a problem until you have clearly identified what the problem is. So here are the guidelines. First, identify all the given quantities and all the quantities to be determined if possible. Make a sketch and label it with any relevant measurements. It's going to be very, very helpful if you try to label the situation. Write the primary equation for the quantity that is to be maximized or minimized. In other words, what's trying to be optimized. Reduce the primary equation to having one single independent variable, and that may involve using a secondary equation that relates the variables of the primary equation in a different way. So determine the feasible domain of the primary situation. Often, you're going to exclude any negative values because most of the time these are real world situations where negative values don't make sense because they're usually talking about time or distance or measurement. But sometimes they're not. So just be careful, look at the context. So basically number 4 is determine the values for which the problem makes sense. 5, determine the desired max or min by using calculus techniques we discussed earlier in this chapter. So at which points on the graph y equals 4 minus x squared are closest to the point 0, 2? Now this is a situation where we're talking about points on a graph. There are no feet, there's not really units to it. So negative numbers would make sense in this problem. So this graph shows that there's 2 points at a minimum distance from the point 0, 2. Okay, because it's a parabola and it's symmetric on either side of the point 0, 2. The distance between 0, 2 and a point on the graph of y equals 4 minus x squared is given by the distance formula. Now remember, the distance formula is basically the Pythagorean theorem solved for the hypotenuse. Another way to think about it is the distance is equal to this change in x squared plus the change in y squared. How they got this was that x is the point, the x coordinate of the point that we don't know, so that's kind of like your x2, minus x1, which is 0, so x2 minus x1 squared plus y2 minus y1 squared. Similarly, the y minus 2 squared came from y2, which is the y coordinate of the point that we don't know, minus the y value of the point that we're trying to get as close to as possible. Okay? Also, we know that this distance formula is in terms of x and y, but we know that y equals 4 minus x squared, so we can substitute that secondary equation that relates y and x to get the primary equation all in terms of x. So we get this. Now, if you simplify this, FOIL it out, and combine like terms, you get square root of of x squared minus 3x squared plus 4. So because d is going to be smallest when the expression inside the radical is smallest, we only need to find the critical numbers of the x to the 4th minus 3x squared plus 4. So the domain of f is the entire real line because there's no limit to how far you can go on the parabola. So there's no endpoints in the domain to consider. But the further you go out on the x-axis, the further away, like if I go out more and more on here, it's going to make this point slide down further and further. It's going to get further away. Okay, but there's like this sweet spot right in here where you're going to have a minimum distance. So f prime equals 4x cubed minus 6x. If I factor that, I get that. And I get 3 possible solutions. 0, square root 3 halves, and negative square root 3 halves. First derivative tests that 0 yields a relative max, whereas both square root 3 halves and negative square root 3 halves yield a minimum distance. So the closest points are square root 3 halves and negative square root 3 halves. And if I plug those back into the original function, I'll get 5 halves. And those are the points that yield a minimum distance. Okay? So find a minimum area. A rectangular page is to contain 24 square inches of print. The margins at the top and bottom are to be 1.5 inches, and the margin at the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So I'm going to minimize the area. Okay, so here's the print. And I want an inch margin on either side, which means I'm going to have 2 additional inches on each side, and 1.5 inch margins on the top and bottom, which means I'm going to have 3 additional inches vertically. Okay, so I want to minimize the amount of paper, which includes the printed page and the margins, and the dimensions of that are y plus 2. So x and y are the dimensions of the printed area, because I know the printed area is 24 square inches, so I could do x times y equals 24. All right. The area that I want to minimize is going to be x plus 3 times y plus 2. It's the dimensions of the printed area plus the margins for each side. Okay, so that's my primary equation. The printed area inside the margins is 24 equals x times y. So if I solve that for y, I get 24 over x. Substitute that in for y in the primary equation. This is what you get. Foil that bad boy out, you get 30 plus 2x plus 72 over x. Be careful when you FOIL, just take your time and simplify it. So because x has to be positive, you're interested only in values of a for x greater than 0. All right. And also, the larger you make x, the smaller that y is going to be. Okay, so if you made x 0, you would have undefined for y, which is impossible. And if you made x like extremely large, y would have to be extremely tiny. So there are no endpoints to the domain. So to find the critical numbers, differentiate, and you'd have 2 minus 72 over x squared. Set that equal to 0 to find your critical number. You get x squared equals 36. Again, when you take the square root, you get plus or minus 6, but since we're in a real life situation where you have measurements, the answer of negative 6 can be thrown out. And the first derivative test confirms that a is a minimum when x equals 6. So when x is 6, y is 24 over 6, which is 4, and the dimensions of the page. Be careful, 6 by 4 is not the answer. That's the dimensions of the printed part. The question asks, what are the dimensions of the page? So the dimensions of the page are x plus 3, which is 9, and y plus 2, which is 6 inches. Make sure you include the units. Also, we're not using implicit differentiation here, or related rates or anything like that. It's just taking the derivative of the area with respect to x. If I take the second derivative, I would get 144 over x cubed. The reason I'm doing that is because I know that the critical numbers are at plus or minus 6, namely just positive 6. If I plug the critical number into the second derivative, you would have 144 over 6 cubed. I don't care what the number is, I just know that that answer is going to be positive. So that's going to be greater than 0, which means your graph is concave up at the critical number, which means you're at a relative min. Okay, so that's the second derivative test, how to just, instead of doing the first derivative test, just to confirm, because the second derivative is so easy to take in this problem, may as well do it and do the second derivative test. Evaluate your second derivative at the critical number. If the second derivative is positive at the critical number, graph's concave up, but you're at a relative min because you tested the critical number. Okay? All right, let's find minimum length. 2 posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are stayed by 2 wires attached to a single stake running from the ground level to the top of each post. Where should the stake be placed so that the least amount of wire is used? So let W be the wire length to be minimalized. So this is what we're talking about. You have a post here and a post here, and you're putting a wire to both posts and putting a stake in the ground somewhere in between. Okay? So W, which is the length of the wire, has to be this length plus this length. So it's just W plus Z. So rather than solving for y in terms of z or vice versa, you can solve for both y and z in terms of a third variable. Because if you think both of these are right triangles, and I can use the Pythagorean theorem, I know that both of them have to be 30 meters apart. If I take x to be the distance that the stake is placed from the smaller pole, I know that that distance is x, and that that is subtracted from 30 to get the distance to the other pole. Okay? So for this one, I have x squared plus 12 squared equals y squared. And from this one, I have 30 minus x quantity squared plus 28 squared equals z squared. Here you go. Which implies that y equals, if I solve this one to get y, is y square root of x squared plus 144. And if I FOIL this out and combine like terms, I get z equals the square root of x squared minus 60x plus 1684. So W is given by w plus, or y plus z. So I add those two. And I know that x has to be between 0 and 30 because x is where I put the peg. So I can either put it at the first post, the last post, or somewhere in between. So continuing on, I differentiate both of those with respect to x, and I get these crazy equations. So letting that equal 0, I get this. And then I put this one on the other side and cross multiply. Okay, you get this. Now here's what we did. We had x over the square root of x squared plus 144 equals negative x minus 30 over the square root of everything that was in there. Now this negative x minus 30, when you distribute the negative, you would have negative x plus 30 or 30 minus x. And that's why this changed to 30 minus x. And then you cross multiply by both of the square roots. And that's why the square root of x squared plus 144 ended up on this side and the other radical ended up on that side. Okay, I hope that was helpful to you. All right, then we just square both sides to get rid of the square roots. And since these are products, when you square both sides, you get x squared times the square root squared, which is just what's inside, times this quantity squared, times the square root squared, which is just this quantity. And now what I'm going to do is distribute the x squared here, FOIL the 30 minus x squared, and then FOIL that with the x squared plus 144 to get all these Batman pajamas here. And then bring all these terms over to this side and cancel out stuff. A lot of stuff's going to cancel out, namely the x to the fourths and the 60 x cubes are going to cancel out, which is really nice because then this just makes this a quadratic. You can factor out a 320 from everything and then factor the rest. And you get x equals 9 and negative 22.5. Well, you could throw negative 22.5 out because x is the distance from one pole to the other, or the distance from the pole to where you put the stake in the ground. So if I test the endpoints, I mean, it's not really going to work because at 0 you have 53.04, and at 30 you have 60.31. If you're at 9, though, the wire is going to be 50 feet long, and you can conclude that the wire should be placed 9 feet away from the 12-foot pole, and the length of the wire you're going to need is going to be 50 feet. All right, and graphing the wire equation, it'll be like kind of like a parabola, and you'll see that the minimum is at 9,50. All right, so from example 4, you can see that the applied optimization problems can involve a lot of algebra. If you would use your graphing calculator, you can confirm that x equals 9 it yields a minimum value by graphing the W equation and just using the calculate feature on your graphing calculator. Now, I will tell you, just doing that is not sufficient for showing your work on an assignment. Okay, so make sure you show the work here, but you can confirm your answers and like kind of check your work using a graphing calculator. All right, let's look at an example where the endpoint yields an optimized situation. So in each of the first four examples, an extreme value occurred at a critical number. That happens often, but sometimes an extreme value can also occur at an endpoint on an interval. So 4 feet of wire is to be used to form a square in a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum total area? All right, so the total area is the area of the square plus the area of the circle. So you have the area of the square, area of the circle. So area of the square is x squared, area of the circle is pi r squared. I also know that I have how much wire? 4 feet to enclose those shapes, which would imply perimeter. So the perimeter of the square is 4x, and the perimeter of the circle is also known as the circumference, which is 2 pi r. So 4 equals 4x plus 2 pi r. Now I'm going to solve that secondary equation for r to get r in terms of x, so that I can substitute that into the area equation to get the area all in terms of just x. So if I solve for r, I got to subtract 4x from both sides, then divide by 2 pi. And after simplifying and factoring, I get 2 times the quantity 1 minus x all over pi. So substitute that in as r for r squared, and that's what you get. And then simplify that a little bit, and you'd have x squared plus 4 times 1 minus x squared, quantity squared, all over pi. Now, you would have pi squared here, but it's going to cancel with a factor of pi here. When you have a product squared, you square each of the factors. So 2 squared is 4, 1 minus x quantity squared is that quantity squared. So I can factor out a pi from all of that. Simplify. All right, and then take the derivative, and this is what you get. So the only critical numbers are at 0 and when x is 4 over pi plus 4, which is about 0.56. So using the critical numbers, and the endpoints 0 and 1. I'm sorry, I said that 0, 1 was a critical number. That's actually the interval that makes sense, because as long as x is between 0 and 1, you can make the figures. Because the square has 4 sides, and if it's a square and you have 4 feet to do it, most each side can be 4. Okay? So notice that the endpoint of 0 equals the maximum 1.273. So when x is 0, that means that all of the wire is used for the circle, because remember, x was the amount used for the square. So if x is 0, then all of the stuff is going to be used for the circle. All right, so let's review the primary equations developed in the first 5 examples as applications go. These 5 examples are fairly simple, and yet the resulting primary equations are quite complicated. We have the volume, the distance, the area formulas, and the wire length. You must expect that real-life applications often involve equations that are at least as complicated as these ones. So remember that one of the main goals of this course is to learn how to use calculus to analyze equations that initially seem formidable. All right, guys, that's it for this section. Please continue on to your assignment, and as always, reach out to me if you have any questions. Take care.